Find and sketch the domain of the following. F of xy is log of x minus 1 plus the square root of y minus x plus the natural log of 4 minus y, all divided by x squared plus 2x plus 1. So this is a problem. It actually comes from an old exam from a few years ago. And you say, okay, so we have some problems. In fact, we have all our sort of basic problems that we often see with these types of things. We see square roots, we see natural logs, and of course we see a fraction, which means that there's a potential for division by 0. So we've got to check all our usual suspects, so to speak. So, all right, we've got to check a bunch of things. So we'll just work our way through. Let's start with the denominator. Well, in the denominator, we just ought to make sure we're not 0. Now, what's another way to say x squared plus 2x plus 1? X plus 1 squared. So, we know our domain, x can't be negative 1, because we want to avoid divide by 0. All right. Now, what else do we have? Well, let's work our way through the top. We have 3 terms. We have to make sure each one works individually. Okay, so log of x minus 1. Well, what needs to be true about what you put into a log? Yeah, so we need that the input, x minus 1, has to be greater than 0. Or, another way to say this is x has to be greater than 1. Square root of y minus x. What do we need? We need the inside to be greater than or equal to 0. Equality is okay, because here you can take the square root of 0, but you can't take the natural log of 0. Or we could say that y has to be greater than or equal to x. And the last part, log of 4 minus y, well, similarly as before, 4 minus y has to be greater than 0. Or we could phrase this as, if we move this across, that, there we go, got to be careful here. 4 greater than y, or y less than 4. Got to be careful with whenever you have an inequality. It's very tempting to get them mixed up. Now, if we think about these individually, so we have sort of 4 pictures here, because there's 4 issues. X not equal 1 says, look, you can't be over here at 1. X greater than 1 says, in fact, you have to be over here. So it turns out that this condition, x not equal to 1, it's redundant. Because if it's true that x is greater than 1, it's also true that x is not equal to negative 1. So it's possible that you have situations where it's like, oh, well, something gets subsumed by a different fact. So, okay. Y greater than or equal to x, well, y equals x, we know that. So that splits us into 2 parts. Well, is above or below? Which one do we need? Because we have that greater than. Are we y greater than or equal to x if we're above, or y greater than or equal to x if we're below? And how can you tell? Yeah, just pick a point. Like over here, here's a point down on that line. Here, y equals 1, x equals 0. Is 1 greater than or equal to 0? It is, it's true. And so that means that that one particular point should be included. But once we know one point, we know everything that's in that same part is included. So we want to be above. And you could also check if you really were wanting to, you could check below as well. All right, y, I guess I should have shaded everything over here, just to be consistent. So here, you include everything except x not equal to negative 1. All right, y less than 4. Okay, so here's 4. And I should mark things. There's 1. And y less than 4 says I'm below. And the thing is, now we do our traditional sort of overlap everything. And what do we see? Well, again, we just need to get these last 3. And what we'll see is we'll have y equal x. So here's that curve, y equals x. Then we'll have up on top, y equals 4. And on the left, we'll have x equals 1. So that our domain is that region there. So you include the points y equal x. That's a solid line. You don't include the dashed lines x equals 1 and y equals 4. And for the corners, you don't include those. The reason you don't include the corners, you might say, well, you do include them on one line, you don't include them on the other line. You say, look, once it's out in anything, it's out. It's out. It's not like, oh, but it works in this case. It can't be the case if it works here. Maybe if it works somewhere else, then somehow it undoes it. No, no. Once you have one problem, you're done. You're out. And so our region now, for our domain, is a triangle. And there you go. All right. Now, of course, we've noted here, you want to avoid divide by 0. And that raises the question, why do we want to avoid divide by 0? We actually talked about this way back a year ago. Why is division by 0 bad? I mean, we're told it's bad, and we're told we don't want to do it, but why? Why do we want to avoid it? What's so bad about it? So, what's the answer? So let's just make a little comment. If I have a ratio, so A divided by B, we say that A divided by B equals C if it's the case that A is equal to B times C. So as an example, 6 divided by 2, we say is 3. Because it turns out that 6 is equal to 2 times 3. So that's one way we can sort of check division. So now we say, okay, suppose we have A divided by 0 equals something. So what happens? Well, it turns out that if A divided by 0 equals C, then following the guideline here, that means that it better be the case that A is equal to 0 times C, which means that 0 times, we get 0. So we lead to two interesting and distinct possibilities. Now, what's one possibility? Well, one possibility is that A is not 0. And I can't have A be equal to 0 and A not be equal to 0 simultaneously. You have to make up your mind. You have to do something. So we can't have A not be 0. So that means like 1 over 0, it's just impossible, doesn't make any sense, and it can't work. But what about the other case? What happens when A is 0? Then we're perfectly fine, right? Because we said A should be 0. So what's the issue? Well, the problem is, if A is 0, what do you choose for C? There's a lot of what's called ambiguity. Anything would work. So 0 over 0, the issue with it is not necessarily that it's undefined, but it's that it's ambiguous. And so a very fancy term you might hear is it's indeterminate. You cannot determine what it is just by that expression. So, well, that's no fun. Well, where do we go? Well, if we can't determine what it is, we'll do our next best thing, which is to say, what should it be? Now, how do we figure out what it should be? Well, when you look at a number in isolation, you can't say much. But you might say, hey, you know, this 0 over 0 is coming from a function where I'm allowed to vary my parameters. And maybe I can say, what's happening nearby? Now, if this sounds very familiar, it should be, because what we're talking about are limits. Limits ask the question, what should happen? So, in particular, we say the limit, as I approach this certain location where I'm getting to 0 over 0. So I take a limit as xy gets close to ab of my function f of xy. I say that I get L out if, as x and y are getting closer and closer to a and b, the function is consistently getting close to L. So there's this sort of notion here. So we're going to be talking about limits today. That's our goal. And we're going to talk about how do we find limits, what are some techniques to evaluate them. And we're going to see that they're so much more interesting when we get up to multivariables. Now, on a side note, there's a technical definition of limits. And the key to understanding the technical definition is to realize that you have these two notions of being close. So we want to say x and y is getting close to a and b. And we want to say f of xy is getting close to L. And so the key is, how do you balance these two notions of close? So the technical definition, which we're not going to test you on, but if you love technical definitions, there's a whole sequence of math courses where we go through and explore this. And we say, well, for every epsilon greater than 0, there's a delta greater than 0. And don't think of these as epsilons and deltas, think of these as distances. So there's a small distance, epsilon. And what is that small distance for epsilon? That's saying how close is f of xy to L. So if I want to have my function be close to that value L, so that's my epsilon, then there's another distance that says as long as your input, the xy minus ab, as long as your input is close, so less than delta, then that will hold. Now you'll notice there's a little piece here, the 0 less than. That basically says we ignore what happens at the point AB. What happens at AB doesn't matter. Because limits aren't about what does happen, limits are about what should happen. Now the good news is a lot of the intuitive properties of limits that we would want to be true are true. So we have some of them listed here. So if we have, say, f and g, and it happens that f is getting close to L and g is getting close to m, then if I add f and g together, they're going to get close to L plus m. Intuitively, that makes sense because we're saying, well, the first part is getting close to L, the second part is getting close to m. Similarly, if we multiply, we say, okay, then individually, f is getting close to L, g is getting close to m, so collectively, they're getting close to L times m. Again, if you divide, something similar happens, as long as it's the case that m is not 0. If m is 0, well, then you have a few things that might happen. If L is not 0 and m is 0, then you're done, your limit does not exist. And of course, if you get 0 over 0, that's our favorite thing that could happen, because what do we do when we see 0 over 0? We get to do more work. It's like, yes, good, the fun continues. You know, good times when we see 0 over 0. And then there's the last thing, which says continuity and limits mix really well. And we should talk about continuity. So a function is continuous. Essentially, if you think back to when we first talked about continuous functions, we did this in Calculus 1. A function is continuous if there are no surprises. So by that we mean the following. If you look at the limit of the function, so the limit is what should happen, and then you compare it to, say, what the function actually does, the answers always agree. That's what continuity means. What should happen and what does happen are the same. And therefore, limits work really nicely. So what this is saying down here at the bottom is that when you have a continuous function, you can pass the limit to the inside. So again, even though I just said it out loud, continuity means what? Well, what should happen is matching with what does happen. So what are continuous functions? Well, continuous functions, we have some nice examples. We start with the simple ones. Polynomials are continuous. So with polynomials, you never get any surprises. So you could have something like x. That's a polynomial. Not very, very astonishing that that's continuous. Of course, you can do some more interesting things. You could have y, because we have two variables, x and y. But at this point, you're thinking that's not that astonishing. Of course, you can have x to the 6 plus 7x squared y cubed plus y to the 17th minus 52 y squared. Anything that's a combination of, like this, powers of x's and y's and mixing them together, these are polynomials. So those are all continuous functions. The sine, the cosine, the arctangent, the exponential, these are all continuous functions. An exponential, for example, that's something like e to a power. So you can have, of course, composition. So you could put e to the x squared plus y squared. That's a nice continuous function. And then you have other functions which are restricted because there are some places where the functions are undefined. So tangent, log, and square root, they're not defined for all numbers. So if you say, look, let's restrict to their domains, then we're fine. So as an example, I could take log of x squared plus y to the 4th plus 1. This is a function which will always be continuous, because x squared plus y to the 4th plus 1, that's a nice continuous function. And I'm putting it to log. And log will be continuous and defined as long as what I plug in is positive. Well, what's true about x squared plus y to the 4th plus 1? Is that always going to be positive? Yeah, it will. In fact, it'll always be at least 1. And therefore, it's going to be always defined. And so once you start having our basic building blocks, you can do all sorts of things. Again, you can do composition. You can multiply things together. So I could say take sine of x cubed, and that's a cubed, times tangent of y plus x. And this will be continuous as long as I avoid the asymptotes of tangent. So there's all sorts of things we can do. Now, what we want to talk about are limits. So there was this note here, we can combine functions. And so we're going to have some tools to evaluate limits. We're going to have some strategies. So the first strategy is to say, if our function is continuous, let's just try plugging in. In fact, this should always be your first go-to if you see a limit. You should say, hey, I have a limit involved. What happens if I evaluate? And you check. Now, what is it that you want to have happen when you evaluate your limit? What's the ideal situation? Yeah, you get a number that makes sense. And most of the time, you want to just make sure that you have something that's not 0 in your denominator. So let's find the following. The limit as xy goes to 1, 1 of x to the 7th y squared plus sine of, and then there's this whole expression on the inside of the sine, cosine of y plus y squared x plus x times e to the y. Then you have x squared plus 3, arctangent of, on the inside, x plus y, plus 4 times secant squared of x times y. Now, the first thing we should check, is this function continuous at 1, 1? Well, we look at our building blocks. We say, okay, we see a polynomial, that's fine. Cosine is continuous, so cosine of y is continuous. If I add a polynomial to that, that's still continuous, so the inside is continuous. Plugging it into sine, that's our composition, that's continuous. X is a polynomial, exponential is continuous. So x e to the y is continuous. We add them up. That's continuous. Similarly downstairs, x squared, that's polynomial, continuous. X plus y is continuous, polynomial. Plugging into arctangent, that's continuous. Secant squared is not always continuous. But where are we at? We're at the point x and y equals 1. Is secant continuous at 1? And the answer is, yeah. So where does secant have a problem? Do you remember? Because secant has asymptotes.
Pi over 2.
Pi over 2. Yeah. Pi over 2, negative pi over 2, 3 pi over 2, negative 3 pi over 2. Essentially, if you take an odd multiple of pi divided by 2, then that's where your problems are for secant. Well, it turns out that 1 is not an odd multiple of pi divided by 2. Okay, so we're continuous. Now, we've gotten to the point that we're so used to continuous functions, we don't even process all that sort of what we just did. We said, oh, well, look, we have our individual pieces. We're putting them together in a nice way. It's become automatic. And that's okay. That's all right. So, what do? Well, the answer is, because of continuity, it says what should happen is what does happen. So we should plug in 1, 1. And now we plug in 1, 1. And we say, okay, we get 1 to the 7th times 1 squared, which is 1, plus sine of cosine of 1, plus y squared times x, which is 1. Then we get plus 1 times e to the 1, which is e. Then downstairs, we're going to get 1 plus 3 arctangent of 1 plus 1, which is 2, plus 4 secant squared of 1. Now, at this point, we say, okay, what comes next? Well, the answer is, we're done. We got a number out. Now, the thing that we should worry about whenever we're doing this is we always say, let's check your denominator. Is this equal to 0? That's the question you always ask. Now, what about the numerator? What if that equals 0? You're like, I don't care. I first want to check to see if the denominator equals 0. If the answer is no, then whatever came out, you're good. Life is good. And you're done. If it does equal 0, then you check to see if the numerator equals 0. And if it's 0 over 0, more work. If it's something that's not 0 over 0, the limit does not exist. Does its denominator equal 0? Well, you might say, I don't know, I'd have to know what arctangent of 2 is, and what is secant of 1. But actually, we can make things a little bit easier. 1 is positive. Arctangent of 2, is that positive or negative? Oh my gosh. I thought everyone knew what arctangent. That's such a cool function. So this is arctangent. Here we go, arctangent. Okay, so arctangent, what happens is it looks like that. So if we're 2, it turns out that if whatever you plug into arctangent is positive, then you get a positive number out. If what you plug in is negative, you get a negative number out. So arctangent of 2, well, that is positive. And in fact, it turns out that you can write arctangent of 2 as arctangent of 2. That's not very interesting, though. It doesn't have a nice value. Like arctangent of 1, that's nice. That's pi fourth. But arctangent of 2 is like, it is what it is. How about secant squared of 1? Is that positive or negative? Positive. Positive. How do you know? Square. Yeah, because you square it. Even if you don't know what secant of 1 is, you know when you square it, it's positive. And if you add up a bunch of positive values, can you get 0? No. So then we're definitely good. Life is good. All right. Well, that's strategy 1. Now, the next one, strategy 2. I like strategy 2. So this one is sort of a little bit different. So here we go. What we want to do is say, hey, you know what? If it's true that a limit exists, then it has to be the case that however I approach my limit point, I've always got to get a consistent answer. So if I approach in different ways and I don't get the same answer, then the limit can't exist. All right, so that's our basic idea. And so how do we use it? Well, let's think back to what happened a year ago. Calculus 1. We would say, hey, look, we're on a line, and I'm trying to approach a point. So this is the point I'm trying to approach. Well, how many ways can I approach it? It's above it's more than 1, but less than 3. 2 is the correct answer. So you had what are called the one-sided limits. So you would, sometimes say, like, channel your inner Beyonce. From the left, as we approach the point, we come from the left. And then you would say, okay, follow that up. From the right, now we're going to come from the right. And then, what would you sing? Now I'm done. I've run out of ways to go to the point. Because there's only 2 things you can do. You can come in from the left, you can come in from the right, and that's it. And so you say, look, if I don't know what's going on, let me just check the 2 sides. And then I'll see whether or not they agree. Now that was the old way. Our old single variable way of looking at the world. Now we're new and fresh, hip and modern. Now I have not just one thing that can vary, I can have multiple things that can vary. So what are some ways I could approach my point? Well, I can still do it from the left, and I can still do it from the right. Is that it? What else can I do? From the top. From the bottom. All right, is that it? Have I run out of ways to approach? No, what else could I do? I can go diagonally on any straight line. And I can do that. All right, is there any other way I could approach? Well, let's see, we've done top, we've done bottom, we've done left, we've done right, we've done every straight line. Is that it? Have we run out of possibilities? Well, if we were 3 dimensions, we could talk about into the board. Right now we're just 2 dimensions. All right, so are we done? Now I should say by now we've come up with infinitely many ways to approach the point. Is that sufficient? Turns out, no. You can be creative. Why go in a straight line? Maybe you had a little bit too much root beer last night and you're zigzagging back and forth. Or maybe, you're trying to confuse your own offense and so you start spiraling around or something. I don't know. But look, the point is you can come up with all sorts of crazy ways to approach. There's infinitely many. Now, here's the good news. This is a wonderful way to show that limits don't exist. Because you say, if I can just find 2 different ways to approach, and they don't agree, my limit for sure doesn't exist. It's a very bad way to figure out what the limit is. Because you'd have to argue you've come up with every possible way to approach. And say, and regardless, you can't come up with a more interesting answer. So most of the time we use this is when we suspect a limit doesn't exist. So we're going to do a couple of examples. So suppose I look at x squared minus y squared, and I divide it by x squared plus y squared, and I say x and y is going to 0, 0. Now if you look at this, this still looks like a continuous function. You've got a polynomial over a polynomial. So the natural thing to do is plug in 0, 0. If you do the natural thing, what do you end up getting? 0 over 0. Which means more work. More work. Good. Good. Well, I needed more work because I was going to run out of space if it was too easy. All right. So what's happening? Well, we need to approach 0, 0, the center. So we need to pick some ways to approach 0, 0. So let's pick a way. How do you want to start? What direction? Okay. So let's start. In fact, we're going to do it from the left and the right simultaneously. Now here's the thing, is when I talk about from the left and from the right, what's really happening here is I'm saying I'm going to approach along a curve. Now what's the advantage? When I approach along a curve is a one-dimensional type object, which means I can simplify it. So really, we can think of this curve, we can really do a parameterization. So this is the curve where my x-coordinate varies, my y-coordinate is always 0. And so I really want to know what happens as t goes to 0. So the advantage that we have is we're going to look at not as two things varying, because here x and y are varying. We're going to look at it as one thing varies. So we're going down to one dimension less. So as I approach here, I say, well, this would be the limit. The t is going to 0. And now I update. Everywhere where I see an x, I put t. Everywhere where I see a y, I put 0. T squared minus 0 squared. T squared plus 0 squared. We can simplify that expression. What does it simplify to? T squared over t squared, which is 1. What's the limit of 1? 1. Okay. So, as we approach from the side, as we approach along that curve, we got 1. So, let's approach from a different direction. And I would suspect that the first two directions you should always check are from the sides and from the top and bottom. So, on that, what's our parameterization look like? 0 and t. So, we're going to take the look at, and here t goes to 0. Limit as t goes to 0. And now, wherever I see an x, I put a 0. And wherever I see a y, I put a t. So we get 0 squared minus t squared over 0 squared plus t squared. Well, that simplifies to what? Negative 1. And the limit of negative 1 is negative 1. And now we're to this point where we say, whoa, one approach gave me 1, a different approach gave me negative 1. And these two don't match. Well, now I'm done. Because if I get different answers depending upon how I approach, then that allows me to conclude that my limit, x squared minus y squared over x squared plus y squared, as I'm going to 0, 0, does not exist. Because I'm getting different answers depending upon how I choose to approach. Okay. So, let's try another one of these. Find the limit as xy goes to 0, 0 of xy divided by x squared plus y squared. All right. How do you want to approach? Well, let's start with the sides. So if we start with the sides, what do they look like? Well, t0. So we're going to take that limit as t goes to 0, and we're going to get t times 0 over t squared plus 0 squared. Well, the good news is upstairs you get 0. So 0 over something is 0, and that limit is 0. If we approach top and bottom, well, in that case, we're going to have 0t. And what do we get? Well, we get a limit as t goes to 0, 0 times t over 0 squared plus t squared, which is the limit as t goes to 0 of 0, which is 0. So, from the left, right, we get 0. From top, bottom, we get 0. All right. Are we done? Is the limit 0? No. We should check more directions. What's something else we could try? Sorry, what? TT. What does that correspond to? The line x equals y. So, approach along another curve, TT. So if we do that, we get the limit as t goes to 0, upstairs t times t, downstairs t squared plus t squared. Well, what does that become if we simplify it? You get t squared upstairs, t squared plus t squared downstairs becomes 1/2. And the limit of a half is a half. Now what? Now we're done. Because 0 and a half are not the same. And once we see that we have two values by different approaches that aren't the same, the limit does not exist. So sometimes it helps to explore a little bit. Okay, let's try one more. The limit as xy goes to 0, 0 of x squared y over x to the fourth plus y squared. All right, how bad could this one be? So let's, I'll speed up a little bit here for this one. So if you approach, let's say, from the x-axis. So that looks like t comma 0. That would be the limit as t goes to 0. And then we'd get t squared times 0 over t to the fourth plus 0 squared. Well, what will this become? It becomes 0, and that gives us 0. What if we approach along a vertical direction? Well, 0 comma t. And if we do that, you're probably going to guess, aha, we're probably still 0. Well, spoiler, you shouldn't tell us that. We should work it out. But yes, it is 0. All right. So, okay, so we approach along two axes. Great. What else should we try? TT. In fact, I'm going to jump ahead, and I'm going to do the following. I'm going to look at this line here, which is t comma k times t. Now, if I'm looking at this, do you recognize what line that is? If you think of t as being x, what is y? K times x. So this is just a line with slope k. So really, this is going to check not just one direction, it's going to check every straight direction we're going to go in. So we're going to check them all simultaneously. Save ourselves, an infinite amount of work. All right. So again, we're checking the t comma kt. So that becomes the limit as t goes to 0 of, all right, let's be careful here. So we have x is t, so that would be t squared. Y is kt. That's upstairs. Downstairs we have t to the fourth, and then plus k squared t squared. Now what can we do here? We can cancel a t squared. So this becomes the limit as t goes to 0 of k times t over t squared plus k squared. Now I should say here that we've already checked the case when k equals 0. So we're going to assume k is not 0. So how do we take this limit? Well, we just plug in 0. What do we get upstairs? We get 0. What do we get downstairs? K squared. But k isn't 0, so our limit is 0. So we've now checked from the left, from the right, from the top, from below, from the diagonal direction. Not just any diagonal direction. We checked every single diagonal direction. We always got 0. So what can we conclude? Well, we can conclude at this point that if there is a limit, it's going to be 0. We haven't concluded that there is a limit, though. See, this is the weakness, is you might come up with something more creative. Now you're probably thinking, how could we be more creative? We've checked all the directions. Well, this is sort of the, how would you even know to check that moment? But bear with me. Suppose we check the following. I'm not going to come along in a straight line. You can kind of see that we were getting dangerously close. If k was 0, we would run into maybe a little bit of trouble here. So we're like, So what we're going to do is we're going to approach along a parabola. So in particular, we're going to approach along the y equals x squared parabola. So in this case, the way you parameterize that, you set x equal t, and y would be t squared. Now you might say, where did the y equal x squared come from? Well, in some sense, you would say, I'd really like these to have the same power, because I want x to the fourth. Well, what could I make y so that y squared looked like x to the fourth? And if you made y be x squared, that would be one way to do it. So let's see what happens. So we take the limit now as t goes to 0, and we plug in x squared, so x would be t, so that's t squared times y, which is another t squared. Downstairs we get x to the fourth, t to the fourth, plus y squared, which is t squared squared. Well, what do we get? Upstairs we get t to the fourth. Downstairs we get t to the fourth plus another t to the fourth. So we get t to the fourth over 2t to the fourth, also known as a half. And that we can take the limit of. And therefore, our answer for this limit is does not exist. Now, one thing you can try, if you're not convinced that this is working properly, is you can say, go into your favorite search engine, say Google. If you type this in, z equals x caret squared, that just means x to the power 2, y over x caret 4 plus y caret 2, and just search for that. It'll actually show you the surface, and you'll see it's a really interesting surface in that there's this definite ridge here that's going on. So it's fun to look at. All right, there's 2 strategies left, and we can probably speed through the last 2 pretty quickly. Number 3, use squeezing to bound things. And you want to bound things from above and below, which are easier to work with. So here we have x to the fourth over x squared plus y squared. Now, one of the things you might get an intuition for is saying, oh, x to the fourth is a higher power than x squared or y squared. So intuitively, x to the fourth should be going to 0 faster than what's happening downstairs. That's good intuition to go with, because it turns out that that's what's going to happen. Now, here's the idea. So we want to bound this above and below. Well, we'll start with the following observation. X squared over x squared plus y squared, well, that's at least 0, because everything's positive. Because I can't take a positive number over the sum of 2 positive numbers and get a negative number. But notice, compare the numerator to the denominator. Which one is bigger? The denominator has to be at least as big or bigger, because if y squared says I'm going to bump you up by a little bit. So this value is less than or equal to 1. So x squared over x squared plus y squared is always between 0 and 1. But I don't have x squared, I have x to the fourth. So how do I make x squared into x to the fourth? Multiply it by x squared. So 0 is less than or equal to x to the fourth over x squared plus y squared. And that's less than or equal to x squared. So what we have is that we can bound the function x to the fourth over x squared plus y squared in between 2 different things. Now, what happens as xy goes to 0, 0? Well, what happens to 0? It goes to 0. That's going to be less than or equal to whatever that is. Well, what happens to x squared? It goes to 0, because that's continuous. You just plug it in. So x fourth over x squared plus y squared, whatever it does, it has to be greater than or equal to 0 and also less than or equal to 0. That's not a lot of wiggle room. There's no freedom to move. So what's going to happen to it? This goes to 0 by squeezing. It has to be squeezed in between. All right, so that's strategy number 3. Now, what's strategy number 4? Take more math classes. All right, limits are tough, but there's lots of ways to approach it. Generally speaking, what do we want to do? Look for better ways to write the function. Maybe you can factor things and get cancellation. Look for ways to bound behavior. And there's a branch of mathematics known as analysis. And in case you're wondering what analysis is, the answer is it's calculus. So you're taking analysis right now. And analysis is the exploration of these things. And it delves into sort of beautiful ideas and more intuition. Now we have just a little bit left, and we have a little bit of time. Where are we going? Well, once we have limits, let's think back to Calculus 1. What was the next thing we did? Derivatives. So we want to think about, all right, where do we want to do? We want to take a derivative. So let's think about how we can get a derivative. So here's the single variable function definition. Limit as x goes to a of f of x minus f of a over x minus a. All right, we'd like to generalize this to multivariable. So we think about the obvious thing and say, oh, here's our first guess. Take f of xy minus f of ab over xy minus ab, right? I mean, that would seem the obvious first guess to do. Do you see any issues here? Numerator we're okay with. Well, what about downstairs? What does it mean to subtract points? Now, you could say it's a difference of points. How do we represent a difference of points? A vector. But where's the vector? In your denominator. Can you divide by vectors? You cannot. Hashtag epic fail. This is not going to work. You can't divide by a vector. It's not going to work. Guess 1 is out the window. And when you say, okay, fine, all right, guess 2, because I'm going to have a backup. The problem was I can't divide by a vector, but I could divide by the length of that vector, because then I can have, f of xy minus f of ab, that's the number, and I could divide by the size of xy minus ab, that's the number, and now life is good, right? This is going to work, right? Right? Wrong. Hashtag subtle fail. Now, it's a little bit more subtle, hence the hashtag. The problem is that mathematics, it's really important to keep orientation. When you take magnitude, you've lost information. You've lost information about orientation, which means neither of these are how we're going to take derivatives. So we're going to talk about how we will take derivatives in our next session, and that's it for today.